Hi, I am Ayush Raj from Indian Institute of Technology, Patna, and we have this paper Autoregressive Adaptive Hypergraph Transformer for Skeleton-Based Activity Recognition, accepted at WACV 2025. All the three authors of this paper are from Indian Institute of Technology, Patna. Now, let's go to the problem definition we are solving in this paper. So, the problem is to recognize human actions from a video, and the data we have for modeling is the human skeleton coordinates data extracted from the video. And this human skeleton can be modeled as a graph with joints being the node and the bone connection between them as edges. And we have the node features as the three-dimensional skeleton coordinates. So basically we have a temporal graph. We have features for each node as the skeleton coordinates. And we need to classify the human action based on the temporal graph. And the motivations we have because of which we took the approach we have specified in this paper is that hypergraphs can capture a higher order relationship between joints for some particular actions like hand waving. There are multiple joints which might not be neighborhood in a graph but involved in a particular action. Or while running, my hand and my legs might have some coordination which might not be captured by a graph efficiently. But hypergraphs can capture these higher order relationships well because multiple nodes can have a single hyperedge. And also for different actions, we need to have different hypergraphs being used in the model because a single hypergraph cannot be used for classifying all the actions. So we need to have input dependent hypergraph being generated in our model. While there are few approaches which generate a hypergraph, but the way of generating hypergraph is not learnable and uh, resorts to some unsupervised techniques in between the model, and this can lead to disruption of the extracted embeddings being learned because of an updation in the intermediate embeddings which is not being controlled by any loss or objective function and becomes an independent part of the model. So here we propose an approach to generate the hypergraph which is learnable, and we also propose an approach to iterate the hypergraph while training. So basically you can see in this picture the hypergraph is being updated with the model parameters during the optimization of model parameters too. In this way, the hypergraph is also being learned and we are not giving some hard-coded input hypergraph. And this is a model agnostic approach which can be used for any hypergraph convolutional network where a hypergraph can be learned through this method. How it is being learned will be talked about in the further slides. And this is just an overview of the different kind of attentions we use in our model architecture. And also we have proposed an approach to dynamically generate a hypergraph in between the model with an objective function which makes it learnable and does not disrupt the features being learned for classification as well. So both of those conditions are satisfied well. And this is our model architecture. So our model contains two blocks, and of the hypergraph encoder block, which is mainly responsible for learning those representations which are relevant for classification. And we have a hypergraph quantizer block in between in the hypergraph encoder block only, which is responsible for generating a hypergraph which is going to be input dependent. And we have a hypergraph decoder block. We're going to talk about this decoder block in further slides. In the hypergraph encoder, we have features learned using hypergraph convolution, and after hypergraph convolution, we do three kinds of attention, basically joint to joint attention and joint to hyper edge attention and joint to bone attention. Now this p vector is a kind of positional embedding which captures the position of a node with respect to other nodes. So it basically has different embeddings for different k, and k is the hop neighborhood. So if a joint has a neighborhood after k hop to the joint j, then positional embedding for I on G will be distinct from others. But for same k, everyone will have the same positional embedding. For a k hop relational relationship, we have a we have same embedding. So these three attention mechanisms are used in this hypergraph encoder block. Now, as we have extracted the features from hypergraph encoder from first two blocks of FHT block, which contains those attention layers and hypergraph convolution, we use those node features extracted to generate a hypergraph, new hypergraph. Now this hypergraph is generated by grouping these embeddings using a codebook vector. So a codebook, basically suppose we have 5 number of hyperedges, then we have 5 codebook vectors, and these vectors are trainable, and these embeddings are just quantized to the nearest codebook vector, and whichever joints belong to a particular codebook vector will be assigned to that particular hyperedge. As you can see, this is in these equations, it can be symbolized mathematically, and we have a quantization loss for training these codebook vectors, and this also does not, this discretization process is not differentiable, so we use a straight through estimator approach during backpropagation, where we just skip this non-differentiable part for updating the parameters directly of the previous part, as done in any discretization process involved in any other model. So this hypergraph generation is not disrupting the features we are getting for further models, because we have a quantization loss involved in backpropagation, which is also optimizing the codebook vectors. Now, more about the hypergraph decoder block. We have a hypergraph attention network which is mainly responsible for generating the weights of different hyperedges, and after we get the weights, we have a hypergraph decoder block which generates a low dimensional representation of all the nodes, which is then applied to k-means clustering, and we get a new hypergraph. Now this part is not the input dependent hypergraph. This is a fixed hypergraph we are learning, which can be distributed across all the actions, and this is being updated after every iteration as the model parameters also get updated. And this is the model agnostic part we have proposed, which can be used for any hypergraph convolutional network. And reconstruction loss is also used because while getting the low dimensional representation as a regularization for the high level features which have been extracted by using hypergraph encoder on the input features. This is our model algorithm. As said, we have a fixed hypergraph, and then that hypergraph is also learned over here in the attentive hypergraph generator, and in between we have the encoder, we have the hypergraph quantizer which quantizes the generated hypergraph in between, and this n represents the nth iteration in which the hypergraph has been updated. So these are the main contributions we have, and this algorithm can give a directed flow of the model architecture. Some of the ablation studies we have done that with different attention mechanisms we have performed what is the incremental increase in accuracy, and the different updating hypergraphs we have done what is the incremental increase in accuracy. We have these ablation analysis, and this shows how our approach beats the previous approaches in different hypergraph convolution or graph transformer methods. The conclusion is that we have this model agnostic approach improving our results. Future scope is to use hyperedge self attention for better results.